To today's lecture. We are going to cover laminar slug flow. Okay, so if you look at the screen, this will be the laminar slug flow. So let us write down first the key concepts. We are going to say that Prandtl number almost equals to 0. Okay, so that means the flow is almost equal, the flow velocity at any point is almost equal and uniform to the inlet flow condition, right. So this also means that the velocity boundary layer or the hydrodynamic boundary layer takes a very long time to develop. So it does not get developed within the length. So the entrance length is basically huge. Not only that, the boundary layer is always thin for the length of the pipe or the duct that we are concerned over here. So of course the thermal boundary layer develops much faster than that. It's a velocity boundary layer which is very thin. Okay, so it's almost like a scenario like this, that this is the velocity boundary layer. There will be a boundary layer obviously. Okay, so the velocity is kind of something like that. Okay, so it's very top hat kind of a profile, and it is almost equal to the velocity u for all practical purposes. It's never quite true, but since the thinness of the boundary layer is so thin that we can effectively imagine that your velocity is almost the same as u. Okay, so we also take that it's a constant wall temperature. The rest are usual assumptions. That means T naught. Okay, there is a uniform inlet temperature, which is T in. These are almost the same as what we had earlier, right. So only thing is that instead of a fully developed velocity profile, which is a function of r, here we have a constant value of the velocity, which is u, mainly because of a situation like this. So this happens a lot in the food industry, because if you are trying to push say solid food or semi-liquid kind of a food through the pipes, okay, there usually the boundary layers are very thin. As a result of that, your velocity is kind of uniform, okay, across the cross section. That means the r dependence is not there anymore. That's what I am trying to say. Okay, but if the pipe is very long, ultimately this velocity profile will develop. Okay, the thinness assumption is going to be no longer valid, but for all practical purposes, for the current situation that we are dealing with, this pipe length is short enough. It's still long, but short enough relatively, so that the velocity remains the same. So as before, we now define our non-dimensional numbers or non-dimensional variables. R bar is equal to R by R naught, X bar X by D, RED into Prandtl number. If you recall from the previous lectures, so G is the non-dimensional variable, which is T minus T naught divided by T in minus T naught being the wall temperature. T naught is the wall temperature, the inlet temperature is T in, right. Remember that we got from our entrance length analysis that X bar is equal to X by D, Reynolds number, Prandtl number. So the energy equation will be U by alpha dt by dx right. That is the standard energy equation that we had, right. Of course, here we are putting u as the velocity instead of the fully developed velocity profile that you had earlier. So u by alpha T in minus T naught divided by d RED into Prandtl number dg by d x bar 1 by r naught square minus T naught. right, after substitution. So let's move to the next one. So if you take the relevant parameters out, or it will be 1/4 dg by dx bar d square g by dr bar square plus 1 by r bar dg by dr bar. Okay. Now, as we know that 1 by x is sometimes written as 1 over the Great's number. Okay. This is written in some of the books. Okay. In other literature you will find, but essentially this is just the reciprocal of the normalized distance. Okay. So, the boundary conditions are g equal to 0 at r bar equal to 1, dg by d bar equal to 0 at r bar equal to 0, g equal to 1 at x bar is equal to 0. You can easily see the veracity of this thing. Okay. So, at r bar equal to 1, okay, where t is equal to t naught. So, therefore, g should be equal to 0, right. R bar equal to 0 should have an inflection point. So, therefore, dg by dr should be equal to 0 over there because of the temperature inflection point. And at x equal to 0, that means x bar equal to 0, that is at the point of the inlet, right, okay, where t is basically equal to t in. So, therefore, g should be equal to 1. So, these are the three boundary conditions that we have. Once again, as I told you earlier, that this equation that you have represents unsteady heat conduction equation, where x bar basically doubles up as the time scale. So, normally in a heat conduction equation or a transient heat conduction equation, right, okay, or 1D transient heat conduction equation, that is what it is, right, in of course cylindrical coordinates, you would have that there will be this term will be basically your time, and this will be the corresponding spatial coordinates, right. So, here of course the x bar is doubling up as your time. So, okay. So, as the axial length is basically what your time scale is all about. Okay. So, it is very equivalent, okay, though the problem is not the same. Okay. So, it is basically an interesting observation nonetheless, that where your 4 x bar is basically like your elapsed time, got it. So, 4 x bar is nothing but like your elapsed time. So, it represents or resembles transient 1D heat conduction equation. Okay, got it. So, the solution, okay, will be kind of similar. So, let us write it in a more put the Great's number. This is the most compact way of writing the same equation. Okay. Once again, you use the separation of variables. So, your g will be basically r1 r bar, z1 4. Okay. So, one is a transient part and one is the spatial part correspondingly. Well, in this case both are spatial, but one is like time. Okay. So, if once you substitute it back into this particular equation, what you have is basically okay, that is what you have, right, okay, or right? Once again, I have told you the significance of choosing minus lambda square. That is because of the reason otherwise you get a exponential term which increases. So here the solution has to be always bounded, right? So you cannot have that exponential increase. Otherwise, mathematically speaking, plus lambda square is an equivalent solution. So, but in this case, from a physical point of view, it cannot be the case. So that's why we have written it like that. Okay, that we covered in our earlier class when we are doing thermally developing flow, right? So it's the same analogy actually works here. Okay, so or Z1 is equal to C1 exponential lambda square by GZ into 4. Right. So that's the first solution that you will have. Once again, you can see that it is exponential and it's negative. So therefore, with time, okay, or with distance, okay, this solution is bounded. On the other hand, okay, so R1 is basically C2 J naught lambda bar plus C3 Y naught lambda bar. Okay, that's the solution. These are basically Bessel's functions. Okay, of course, as you can see, it is of the order 0, so 0 order, right? Okay, first kind, second kind. Okay. So J is the first kind, Y is basically the second kind. Okay, so that's the solution that you have. Okay, but once again, one interesting thing about this particular solution is that let us look at the companion PPT. So if you look at now a situation like this, right, where we have basically plotted the functions, right, and I have marked a few things over here. So as you can see that at this particular term, okay, y is basically the second kind, okay, at 0 it goes to minus infinity, okay, but you know that your g, because r is basically a combination, if you recall what we did just now was basically that you had r, right, you had r1, if we write it here, then it is equal to J naught lambda r bar plus C3 Y naught, okay, lambda r bar, correct? These are the two things that we had just now, right? Of course, as you can see, at r equal to 0, therefore, or r bar equal to 0, right, this particular term basically blows up, right? That is because it goes to infinity, right, from what you can see over here, there is an infinity, right? So, in order to assure finiteness of G, because what is G? G is basically nothing but R1 into Z1, right? That is G, right? R1 into Z1 is G, right? So, in order to keep G finite, okay, finiteness of G, what we can technically assure in order to do that is basically to make C3 equal to 0. So, C3 has to be equal to 0. Because otherwise this entire term will blow up at r bar equal to 0, right. So that is the logic that we will apply over here and make that C3 therefore should be equal to 0, correct. Okay. So moving on, going back to our journal. So therefore your r here in this case C3 must be equal to 0, right. Okay. So therefore, your total G will be now C exponential 4 lambda square by Gz into J naught into lambda r bar, right, combining the two constants, okay, and assuring that C3 is equal to 0, right. Now, of course, you have G equal to 0 at r bar equal to 1, correct, okay. So this of course implies that J naught at lambda, okay, is equal to 0. There's many values of lambda, right, okay. So therefore your G should be equal to n equal to 1 to infinity Cn exponential minus 4 lambda n square Gz J naught lambda n into r bar, okay. Got it? Okay. And j naught into lambda n is equal to 0. Got it? So, multi-values of lambda n. Okay. Also at 4 by gz is equal to 0, g is equal to 1, that also we know, right. So, therefore, n equal to 1 to infinity Cn j naught lambda n r bar is equal to 1. Got it? Okay. Now, taking this forward, okay, therefore, G is equal to 2 into n equal to 1 to lambda e 4 lambda n square into gz j naught lambda n r bar divided by lambda n g1 into lambda. Okay. This is of the first order, okay, Bessel's function of the first kind. Okay. So, Gm, which if you recall is the mean temperature or the mixed mean temperature, that is given as T naught minus Tm divided by T naught minus T in, right. Okay. So, that is a mixed mean temperature that we have. Okay. Got it? So, Gm, in order to evaluate that, okay, we already know how to do it. It is integral 0 to 1 g r dr, right. That is what it is. So, 4 0 to 1 exponential minus 4 lambda n square by gz r bar j naught lambda n r bar lambda n j1 lambda n into dr bar. Therefore, Gm would be equal to 4 okay, that is Gm for you. Got it? Okay. So, that will be Gm, that is the mixed mean temperature what we defined. Similarly, your Nusselt number, which will be one of the most important parameter over here, okay, will be, see, all these series converges pretty fast. So, you do not need to consider a whole lot of terms, right, to get convergence. Okay. So, this is the value of Nusselt number at any point, right. Obviously, as x bar approaches infinity, right, okay, what happens is that your Nusselt number, this particular form, approaches 5.7831. It is a little higher than your other cases. That is because you are dealing with a uniform flow field right now. Okay. So, so this is the key value, and of course, we have in the PPT, we can show that this is how the entire thing actually works. As you can see, this is the mixed mean temperature, okay, and this is the corresponding value of Nusselt number. Once again, it starts off pretty high at around x bar is equal to 0.1, right. It slowly asymptotes to the value of about 5.7831. Okay, and after that it is constant, because that is the thermally developed regime. Okay, and the only thing is that here u is equal to capital U. Okay, so that is the only caveat that we have in this particular case, right. Okay, so that is interesting. So you should note the difference between this and the corresponding situation where the velocity profile was not like this. Okay. I would pose the problem because for the constant constant wall heat flux for the same situation, right? But you can solve it on your own. Once again, the flow is a slug flow. Prandtl number goes to 0. Inlet temperature is uniform. This is uniform, right? Okay, there is a uniform wall heat flux. That's the only difference, which is Q double prime. That is all. There is a uniform heat flux, which is given by Q double prime. Okay. So now your definition of G is T minus T in divided by Q double prime R naught by K, right? R bar equal to R by R naught. X bar is equal to X by D divided by RED into Prandtl number, right? Okay. Okay. So those are the things that we have. Okay. Then you have your U by alpha dt by dx is equal to d square t by dr square plus 1 by r dt by dr. Okay. The same thing is valid now over here, except now your U becomes once again capital U. Q double prime now comes over here because of your definition. This dg by dx bar, right, is equal to Q double prime R naught by K R bar square plus 1 by R bar dg by dr bar, right. Now if you take a few terms off from both sides, okay, once again your equation remains exactly the same. Of course, the boundary conditions will be different, as you know. R bar square plus dg by dr bar, okay, into 1 by r bar, right. Only thing is that, so nothing has changed as far as the equations are concerned. They still are the same, except now the boundary conditions are a little bit different. So G at x bar equal to 0 is equal to 0. That is obvious once again, okay, because your T in, T is basically equal to T in, okay. In that particular case, dg by dr bar at r bar equal to 0 is 0 because of the finiteness of the whole thing, okay, and dg by dr bar at r bar equal to 1 is equal to 1 now, okay. That is because your heat flux, okay, because you have a constant wall heat flux now, okay. This is because your K dt by dr is equal to Q double prime, correct, okay. That is because of that. So the equations, as I said, okay, the only boundary condition that has changed is this guy over here, and your definition of G also has undergone a change, right. So based on these two factors, that your G has undergone a change and your dg by dr, you have to write the flux conditions like that, okay. The rest of the problem can be worked out exactly in the same way as before, because this part of the equation does not change at all. It's just the boundary conditions now that you have to apply, and then you have to see what kind of a answer that you get, okay. So that is what is left as a task, but I have posed the problem and shown how the problem actually works. Nothing more changes, except please note that now this is the way that we have written it, okay. So here what we do is that in this particular lecture we have covered the uniform slug flow, in which we have shown that though this is an unrealistic situation, but for all practical purposes the boundary layer remains small throughout the entire span of the pipe length, okay, then perhaps this is not a bad approximation, okay. It might over predict the Nusselt number by a little bit, but that is okay so long, because your analysis is very simple, right, and it almost represents like a transient heat conduction equation, as we saw, right, where the conduction term is, axial conduction term is, or the time varying conduction term is basically the axial conduction term, okay. So based on this we have formulated, we have shown that the limiting case of Nusselt number, at least in the case of constant wall temperature, is 5.78, which is higher than the Nusselt number for both the other cases, okay. That means for uniform heat flux and uniform wall temperature for the fully developed thermally and hydrodynamically fully developed flows that we did much earlier, right. Okay. The solution is a little bit onerous in the sense that it involves separation of variables and series solutions essentially, right. But as we know that though there are infinite number of terms, the series converges usually pretty fast. That means the terms do not change, progressively get smaller, so that you do not have much of a change as we include more higher and higher order terms. So, within 4, 5 terms, 6 terms, you basically have convergence. Okay. So, in the next class what we are going to do is that we are going to look at the viscous dissipation part just a little bit, and we are going to pose the problem of power law fluids. That means fluids which may have which is not a Newtonian fluid by nature, right. So, they have got a power law behavior. This is not a rheological flow course. That means it not deals with rheology or complex fluids. What we are going to do is a very straightforward. There is a lot people can spend an entire course on rheological flows, how the rheological flows actually, the convective heat transfer mode of such flows, okay, where shear is not such a simple function, okay, of viscosity. But in this particular case, we are just going to give a simple example and see how those problems can be tackled and move on. Okay, if you want a more full-fledged course, you should consult, convective heat transfer or heat transfer in complex fluids. Okay, thank you. In the last class, we started doing the scaling analysis, and if you remember correctly, that we had 2 ranges. One was for Prandtl number greater than 1 and one was Prandtl number less than 1. And we said that in these Prandtl number ranges, okay, which particular terms become most important. So, let us write the governing whatever we did in the last class. So, it was something like this. Okay. So, then there was the friction term, and of course, this is buoyancy. So, this is basically was our buoyancy term, right. Okay. So, this was the friction or the viscous term, and this was the inertia, right. So, depending on the value of your Prandtl number, okay, we can have different types of scenarios, right. So, let us take the high Prandtl number fluid, which means its Prandtl number much greater than 1. We are going to propose a 2 extreme type of solution over here. Okay. So, when Prandtl number is much greater than 1, friction, so friction is basically balanced by the buoyancy. Okay. So, friction and buoyancy kind of balances each other. Okay. So, in other words, these are the 2 terms which basically balance each other. So, in that particular case, your value of your delta T, okay, which is basically the boundary layer thickness, will scale as H RAH to the power of minus 1/4, right. Remember the scale, it is not Rayleigh number that is important. It is Rayleigh number raised to the power of 1/4, minus 1/4, that is the term which is important. So, the correct scaling comes from that. Okay. So, delta is, or delta by H, in other words, is nothing but some kind of a slenderness ratio. If you recall that if this was your boundary layer, this is the plate, correct. Okay. So, this is your delta T, right, if you recall, then delta T by H, okay, is basically nothing but the slenderness ratio. This is the same type of thing that you would see in your flat plate boundary layer forced convection, where it was delta by X, right. It was, in that case, the plate was basically oriented in the horizontal direction and it was forced in nature. So, delta T by H and delta by X, okay, basically represents the kind of slenderness ratio. So, here the slenderness ratio essentially scales as Rayleigh number to the power of 1 minus 1/4. Okay. So, the heat transfer, as we know, the heat transfer coefficient H basically scales as K over delta T. This is still the same, it is inverse of the boundary layer thickness, right. So, the Nusselt number in this particular case is this, okay, where H being the relevant length scale of the problem, and this represents RAH to the power of 1/4, right. Okay. So, this is an interesting thing. So, the Nusselt number varies as Rayleigh to the power of 1/4, the boundary layer thickness varies as RAH to the power of -1/4, right. Okay. Now, the problem does not really end here. Okay. The problem is a little bit more complicated than this. Okay. So, let us, before we go into that, let us also calculate that what is going to be your V, that means the velocity scale that is imposed by this temperature gradient. Now, that velocity scale is given by alpha by h into Rayleigh number h to the power of half, right. Okay. So, V is alpha by h multiplied by Rayleigh number h to the power of half. Okay. So, these all comes from the scaling arguments, this all comes from the scaling that we did earlier, right. It is just a substitution of delta t, that is all that we have done, okay, to get from here to here. Okay. So, now that you know this, now the question remains, what will be the velocity profile look like? Because remember, last time we kind of sketched and we said that we are going to change it, that the velocity profile is going to look something like that. Okay. But in reality, does the velocity profile exactly looks like that, or is it something a little bit more different than this, right? Okay, because last time what we said was that at the wall it must be 0, at the edge it must be 0, so it must have a maximum somewhere in between, right. So, that was the whole argument that we pursued, right. Okay, so, in that particular case, to answer this particular question, okay, let us see the situation a little bit more carefully. Okay, and this is where the plot actually thickens a little bit. Okay. So, these are the two things. Okay. So, this is, let us mark something like a delta t here. Delta t is nothing but the temperature differential that is creating the problem. This is your delta t, which is basically the boundary layer thickness. Okay. So, in this particular zone, for Prandtl number much greater than 1, right, for Prandtl number much greater than 1, okay, if you look at in this particular situation, okay, towards the left side of this delta t or within this delta t, it's like delta t from here to here, right, what you are going to get, the temperature is going to start at the delta t, that is the maximum. It slowly goes down to something like 0 here. Okay. It's more asymptotic. Okay. Okay. So, that is the temperature profile, correct. So, here in this particular zone in the driving heated layer, this is the driver, right, because beyond this there is no temperature gradient, it is T infinity, it is T infinity here. Right. So, the temperature decays naturally, it takes heat from the wall, okay, it naturally decays, okay, and it goes, the decay amount, okay, is basically 0, that means you go and reach the T infinity, okay, after the delta t is over, right, that is standard whatever we know about boundary layer. So, therefore, the driver for this particular problem is essentially this heated layer, right, whatever the air, whatever gas that you are talking about, whatever is getting heated in this region around the wall is basically the driving mechanism for this buoyancy, right. And here you have a balance between friction, because it is a Prandtl number much greater than 1 problem, balancing the buoyancy, correct. That is the nature, right. Okay. Now, what about the velocity now? The natural question is that, okay, now we have a situation in which, you know, the temperature decays, okay, it is gone, right, but what about the velocity now? Okay. So, how would the velocity boundary layer, because remember it is a Prandtl number much greater than 1 situation, okay, naturally. Okay. So, what happens in the region which is to the right of this delta t? Okay. Of course, the temperature does not exist anymore. So, in this particular region, okay, if we say that this is a driven layer, almost like an added mass effect, right, that when you have something moving it carries, okay, some of the added mass with it. Okay. So, this is a driven layer which is unheated, correct, it is unheated because there is no temperature gradient over there. So, in that particular case, what is actually driving that driven layer? What will be the forces that will actually act in that particular region? One thing that you can be sure, it has to be inertia, because there is a motion that is created, right. So, that motion now has to be balanced by the friction. There is no buoyancy here, right. That motion has to be balanced by the friction, right. So, in this particular case what will happen is that if we mark the scale of the velocity, if this is the scale of the velocity, this velocity will grow and this will decay at a certain distance which is given by delta, right. So, this delta is this. So, delta is definitely greater than delta t, okay. It is a Prandtl number much greater than 1 situation, remember. Okay. Now, the scale of the velocity and the scale of the velocity is driven, remember here two things. One is that the velocity scale is determined by the heated driving layer, right. Okay. But on the other hand, the driven layer thickness or the total thickness that you are actually dealing with, okay, is basically determined by this balance between inertia and friction, okay, outside of this delta t. So, in other words, in this region, okay, if we just apply a balance between inertia balances friction, okay. So, what we will have is basically v square h balancing gamma v by delta square, correct. Now, that will be the balance, okay. Now, if we already know what is the scale of v is, right, that we just did. If you just go to the previous one, so that is the scale of v, this is remains unaltered, alpha h by Reynolds number to the power of half, okay. So, you substitute v equal to alpha h, okay, or Rayleigh number to the power of half, okay. You substitute that over here in this particular equation, right, okay. What you get is basically your delta scales as h RAH minus 1/4 Prandtl number half, okay. So, imagine this, what was your delta t per se? Delta t was h into RAH to the power of minus 1/4, right, that was your delta t. So, basically the length scale is still h into RAH to the power of minus 1/4, it is just that you have added a stretching factor, okay, with respect to the Prandtl number. So, Prandtl number basically acts like a stretcher, okay, a stretching factor over here, okay, that actually leads to this particular problem, okay. So, in the Prandtl number much greater than 1 situation, okay, to recap, you have basically two zones, right, okay. The driving heated layer is basically a balance between friction and buoyancy, right, where the relevant thermal boundary layer is delta t, right, and the velocity scale comes from this particular analysis, okay, which is given over here, right, and the Nusselt number is also given in the same way. However, the driven portion, that is the layer that is driven because of this flow that is created and because it has got a Prandtl number which is much greater than 1 effect basically, okay. What we have is that we have a second region in which there is an inertia and friction balance, okay, because there is no buoyancy over there is no temperature gradient. So, how can there be buoyancy, right. From there you find that your boundary layer, your velocity boundary layer is basically stretched a little bit. How much it is stretched is determined what is the value of your Prandtl number. If your Prandtl number is very high, you can see from this equation right here about delta, if your Prandtl number is very high, this velocity effect is felt for a very long distance, got it, even though this layer may be very small, understand. So, the driving layer is very small, but the driven layer can be quite large, okay, depending on what is the value of your Prandtl number. If your Prandtl number is very high, it can be felt over a very long distance, right, okay. So, but ideally speaking, okay, so here of course your delta by delta t, okay, is basically a Prandtl number to the power of half kind of a relationship, right, if you divide the two and it is greater than 1. So, this is one of the important relationship that you should recognize here. Therefore, unlike in a momentum boundary layer, the velocity boundary layer is determined by two scales, okay. One is your delta and one is your delta t, There are two scales which determines it, delta and delta t. This is obvious because your momentum equation now has got the inbuilt temperature, right. You have got the inbuilt body force term, okay. In terms of temperature now, the buoyancy and the body force term combination, in terms of the temperature in the momentum equation inbuilt, right. So, it is very natural, right, that your velocity profile is now going to be determined by a two parameter kind of a set. So, it is delta and delta t, right, unlike in forced convection, okay, where it was not, it was decoupled from delta largely, right. There is, unless there is some property variation that you are taking into account, okay. So, the velocity scale is reached within this delta t, because you can see the peak is appearing within the delta t, right, okay. Whatever happens beyond that is basically the decay of the tail of the velocity, because where inertia and friction are basically fighting among each other, right, because you know the Navier-Stokes is a dissipative kind of a system, okay. Got it. So, based on this we move to the next one, which is basically the low Prandtl number fluid. That means Prandtl number is much less than 1, okay. So, here of course your delta t scales as h RAH Prandtl number to the power of -1/4. That was the old condition, remember, and here of course is a balance between inertia and buoyancy. Right. That is what we told, that it is a balance between inertia and buoyancy, because Prandtl number being much less than 1, inverse of the Prandtl number is much greater than 1. So, therefore, the friction term does not really become very important here. Okay. So, V, okay, or the velocity scale that is introduced is alpha by h into RAH into Prandtl number to the power of half, right. That is the velocity scale. And the Nusselt number is once again the same, but of course it has got the Prandtl number now, right. Got it, right. In some cases this Rayleigh number into Prandtl number combination is given by a new number which is called Boussinesq's number, okay, BOH, okay. So, you can write this term as Boussinesq's number to the power of 1/4 as well, okay. All the places where there is Rayleigh number into Prandtl number combination, you can write it in terms of the Boussinesq's number. So, the Boussinesq's number is basically given by G beta delta t h cube divided by alpha square, right, okay. Okay. So, for low Prandtl number fluid, it is the Rayleigh number which is important, right. For high Prandtl number fluid, it is the Rayleigh number which is important. For the low Prandtl number fluid, it is the Rayleigh number and Prandtl number combination that is important. Got it? Okay. Which we have cast and written it as Boussinesq's number, right. Okay. So, also here of course, once again if I try to draw now this particular system, right. So, what this particular system will look like, right. So, that is the natural thing, that the natural question that pops in one's mind. So, let us look at that situation. Okay. Once again it is a Prandtl number much less than 1 system. I will put a few lines and we will go through it as and when. This is delta t, okay. This is the temperature differential, okay. So, it comes down like this, kind of like that, okay. Got it? This is basically a balance between inertia balancing buoyancy, right. Inertia balancing buoyancy. We have not said anything about the velocity scale though, okay. So, this looks very natural, that once again it decays to some kind of a 0, right. The profile looks a little bit different, it looks a more linearish kind of a profile, but that we will see that why that thing happens in that particular way. Okay. So, based on this you have a very clear idea that this is how the temperature profile should actually be. Okay. Now, outside this delta T, of course, okay, because this is a situation in which we are dealing with a problem in which the friction is not important in this particular layer, right. So, beyond this delta T, remember the difference between the last situation and this, beyond this delta T once again buoyancy goes to 0, right, the buoyancy goes to 0, right. So, in this particular region beyond delta T, because it is a low Prandtl number fluid, right, okay, there is no velocity possible outside this particular layer, correct, okay, because it is a low Prandtl number fluid, its inertia driven by buoyancy, inertia buoyancy buoyancy are balancing each other. So, beyond this of course, the buoyancy is obviously going to be 0 because there is no temperature gradient to support it. So, naturally there is no velocity scale that are possible. Okay. So, the velocity profile, okay, must be then as wide as the temperature profile, that is about it, right. It must be as high as the temperature profile, right. Okay. So, that means whatever the velocity profile we are going to draw, it should have a maxima somewhere, and it will be 0 on this side and 0 on the wall side. Wall side it has to be 0 regardless, right. On this side it will be 0 because there is no driving mechanism and friction is not important in that particular region anymore, and it is a low Prandtl number fluid, right. So, the effect of momentum is not felt up to that particular region, got it. Okay. So, the velocity profile must be as wide as the temperature profile, okay, and so we can write this velocity profile must be as wide as the temperature profile right, it should be as high as the temperature profile. So, naturally this dictates that the peak of the velocity would be somewhere in between these two limits, right, these two 0 and delta T. In this limit the velocity must be maximum in some particular some location, right. Okay. So, velocity should have a peak, somewhere in between, right, has to be, right. Okay. So, the location of the velocity peak is a important second length scale that comes into this particular problem. Okay. So, location of the velocity peak is an important second length scale. Okay. So, if we assume that delta V is that particular thickness, it is a very small thickness of a layer right next to the wall. Just hear the arguments here very carefully, that we are imagining that there is a thin layer of fluid very close to the wall, right, and that we are defining as this delta V, because we are trying to find out what will be the location of the peak, right, what will be the location of the peak and what will be the value of the peak, right. Okay. Now, in this particular location, in that small band, what is important? The most important part over there is your friction can no longer be taken to be equal to 0, because it is a region very, very close to the wall, right. It is a region very, very close to the wall where the shear is very, very important, right. So, there the friction cannot be neglected, right. What can be neglected though in that particular region is the inertia, right, okay, because it is a region very close to the wall, right. So, by the concept of your boundary layer and whatever you have learned in the course of this particular course, okay, it is basically the friction, okay, in that particular layer which is balancing what we call the buoyancy. So, friction and buoyancy basically, okay, balance each other in a layer, okay, which is very, very close to the wall, in a very thin layer which is called the delta V, okay, in which the buoyancy driven fluid is restrained by the viscosity of the wall, right. That is essentially in a nutshell what friction balancing buoyancy exactly means, right? Okay. So, there if we now apply our scaling argument, right, in that particular region, so in delta V, in that region, if we apply the scaling, okay, that is the scaling that we have, right, that is buoyancy and this is friction, right. So, from there you can devise your scale will be something like this, right, where this GRH, this parameter that you are actually seeing, okay, is basically Rayleigh number divided by Prandtl number, right. In other words, it is written as G beta delta T H cube divided by gamma square, right. In other words, this is called the Grashof number. Right. Okay. So, this is called the Grashof number, right. In other words, the delta V, that layered thickness that we have found out, this second thickness, okay, is given by once again H into the Grashof number. Grashof number is Rayleigh number and Prandtl number. So, once again you see that the scaling is still Rayleigh number H into Rayleigh number to the power of minus 1/4, and it has been compressed, okay, or changed by a factor involving the Prandtl number. Once again that particular, as I told you earlier, it is a stretching or a compression term, that is what Prandtl number is, right. So, you have a scale, using that you are just compressing it like this or stretching it out like this, that is what you are doing with the Prandtl number by dividing it or multiplying it, right, and that is exactly what we have done over here, right. So, there are three numbers that emerges out of this discussion, right. Rayleigh number, which is valid for high Prandtl number fluid analysis, right. Then for low Prandtl number fluid analysis, there are two further numbers that comes into the picture. One is the Boussinesq number, okay, which determines what we call the thickness of the temperature boundary layer, the first length scale of the problem, okay. The second length scale, okay, which is the thin layer in which the velocity basically peaks, okay, that is taken care of by the Grashof number, okay, which is nothing but the Rayleigh number divided by Prandtl number, right. So, it is once again a stretching term that we have applied over here. So, naturally before we end this particular lecture is basically what will the velocity profile look like. So, it will peak somewhere there and then it will slowly kind of decay like this. Something like that, okay. So, it will peak somewhere there. So, this is your velocity scale, okay, and that location of that delta V is given by the Grashof number, okay. So, this has been our grand findings, so to say, okay, and of course, your delta V by delta T like we wrote before, okay, is once again Prandtl number to the power of half, okay, and this time it is less than 1, right, okay. So, clear and up to this particular part. Now, we will show some observations based on this, okay, in the form of a table, okay. But up to this particular point it is clear three numbers, Rayleigh number, Boussinesq number and the Grashof number, okay. Now, in many of the books this will be represented that rather than stating these numbers as ratio of forces, right. For example, in this case Grashof number you can see from the definition, okay, it is a balance between the friction and the buoyancy force, correct, because that is how we got it in the first place, right. Similar in Boussinesq number and Rayleigh number, you can just look at the scale arguments, right. But in some cases people look at it like what we call the slenderness ratio, that means the ratio of the boundary layer thickness versus the natural length scale of the problem, right. So, the ratio of those two is what actually gives you the that is what the significance of these numbers are, okay. But in many cases, okay, you will find the other interpretation, that is because it is a ratio of the two scales. I mean either it is the two forces basically, buoyancy friction, okay, buoyancy inertia and things like that, okay. So, it is just the balance between all these forces, okay. So, in the next class what we will do, we will start with the observations, okay, and then look at the integral formulations in a little bit more details, right, okay. So, that was what we are going to do. and we saw that what will be the requirement for natural convection. So, in this particular class we are going to start it off with some of the formulations. So, we write down the governing equations first, and from the governing equations let us see that how we can basically through scaling and other arguments establish the relevant parameters that are responsible for driving this natural convection. Okay. So, our equation sets will be steady 2D equations. Okay. Our delta T, which is basically, if you consider this as your wall, which is at a temperature T naught, and delta T is basically the layer. So, let us assume this for the time being. So, this is your delta T. Okay. So, H being the height. So, H is much greater than delta T. Okay. So, here the driving factor, as we mentioned earlier, factor is gravity plus the density variation. The gravity is an important parameter over here. Okay, the outside fluid is at a temperature T infinity, T naught is greater than T infinity. I mean, these are the cases under this considerations we will solve. So, the first, the continuity. So, the continuity equation is, once again, if this is x, this is y, this is u, this is v. Okay. So, dux by dy plus dv by dy is equal to 0. First continuity equation, then comes the momentum equations. Okay. The momentum equations, of course, there are two momentum equations now, v du dy. It is exactly the same, so there is not much to describe. E square u dx square plus d square u dy square. Okay. So, this is in the momentum in the x direction, no gravity comes into the picture, gravity is acting downwards. Okay. On the other hand, got it, minus g, g is the additional term that you have, right. Okay. So, up to this, of course, we have just, and then of course, the energy equation is du dt by dx plus v dt by dy alpha d square t by dx square, right. Okay. So, x momentum, y momentum, continuity, these are the equations that you have. This is a part of the y momentum at g. So, this is the only additional term that you see over here, which you are not have not seen the same in the case of forced convection, because forced convection is forced. So, gravity is not gravity, gravity is too small for those things. Okay. Of course, forcing can be important, gravity can be important in certain situations in forced convection also. Let us not make a sweeping comment about that, but normally in most of the problems that we dealt with, we did not consider that to be the case. Okay. So, we do the boundary layer approximation, right. So, the boundary layer approximation, so where we say that P is a function of y, right. This is the same thing that we did earlier, okay, that P is not a function of x, it is only a function of y. Remember our flat plate boundary layer, there of course the axes were a little bit different. Okay. So, but based on that you get what I am talking about. Y scales as h, that is the height, x scales as delta t, right, and dp by dy is equal to dp infinity by dy is equal to minus rho infinity into g. So, it is essentially hydrostatic in origin, got it. So, P is only a function of y, that it has to be, right, because P is not a function of x. This we already proved in our flat plate boundary layer problem, right. Now, in this particular case obviously, okay, because it is gravity assisted, okay, this particular pressure drop is nothing but the given by the hydrostatic head, that rho infinity g is nothing but the hydrostatic head over here, okay. And also d square by dx square is much greater than d square by dy square, right, because y being the direction of the flow and x being the boundary layer direction, so, or the depth of the boundary layer direction. So, naturally this parameter will be also satisfied, all right. So, therefore, the y momentum equation, which is the most important equation here in this case anyways, okay, is basically given as d dv by dx plus v dv dy, okay, equal to minus 1 over rho dp infinity by dy, okay, plus gamma d square v dx square minus g, okay, minus g. Now, you are going to substitute this back here, that is what we are going to do. So, and we are going to take the rho to the left hand side. So, what will happen is that u dv dx plus v dv dy equal to mu d square v dx square plus g rho infinity minus rho, right. Okay. Rho infinity is basically the density of the fluid at T infinity, right, in the reservoir section, right. So, this is the equation, this is the y momentum equation. Now, here as you can see, two interesting things comes out, okay. So, there is a rho here, there is a rho there, right. So, ideally for a system like this where the rho is actually changing, right, you have to incorporate the change everywhere, right. So, that means this rho, now we have to cast it in terms of rho infinity and see what kind of a variation we get, or cast it in terms of temperature, right, because that was the argument, that if the temperature is driving the density, then we have to cast density in terms of temperature, right. Now, and that we will use that beta that we already have, right, that gives you the relationship between density change and temperature change. Now, interesting point to note over here is that here you have actually a density rho, here you once again have a density difference, which is basically like the buoyancy type of term that you have, right. Now, in this particular situation, looking at this, you would ideally say, okay, let us substitute whatever is the density change here as well as whatever is the density change here, right, and this will make the problem a little bit more complicated than what we anticipate, right, because density on the left hand side is associated with the convective term, right, density on the right hand side is associated with the buoyancy and the body force term, right, it is associated with the body force term. So, we make here an assumption, okay, which is going to be valid for small temperature differences only, and that approximation is called the Boussinesq's approximation. So, what does Boussinesq's approximation entail? We will come to that in a little bit. Okay, Boussinesq's approximation actually tells you, or the spirit of the Boussinesq, let us put it as the spirit of the Boussinesq's approximation. The spirit of the Boussinesq's approximation is that the density on the left hand side, that means associated with the convective terms, okay, let us take that to be the same density as the reservoir fluid, right. Let us take that to be constant, okay, point number 1. Point number 2 is that the density on the right hand side, let us now express that density in terms of temperature. So, you see that we are differentiating the problem, we are stating that this is still an incompressible type of a problem. That means, most part of the Navier-Stokes equation is actually behaving with the constant density term, right. However, in the body force term, when density is present, okay, we are taking its variation into consideration, okay. So, that is the thing that Boussinesq approximately did, okay. So, what happens is that now let us see that what the density will be. So, density is given by rho. So, if you take it to be expansion, okay. So, just take a first order expansion in this particular case, okay, beta t minus t infinity plus there are a lot of higher order terms, right. This essentially tells you that beta is basically a linear, that slope, if you recall, that beta is nothing but 1 over rho d rho by dt at constant p, right. What we have done using this expression and this expression, combining these two, this actually tells you that beta is basically a linear slope. That means, you take rho minus rho infinity divided by t minus t infinity, you get beta, right. So, it is like a linear interpolation of the whole thing, right. You are not taking into account any second order curvature effects, right, square terms that we have over here. So, this can only happen, this can only work when the density or the temperature difference is small. That means, T is basically T infinity plus some epsilon, okay. So, it is small. So, the variation in density is small. T equal to T infinity minus epsilon, variation in the density is actually small, understood. So, this can only happen when you actually take only the first order terms, right, okay, the leading order term, right, okay. So, if you now substitute, okay, so if you substitute the whole messy looking thing now in the governing equation, what you would normally expect to get is something like this, right, 1 minus beta t minus t infinity, that will be the first term, u dv dx plus v dv dy, right. This will be the total form if we write it like this, mu d square v dx square plus g beta t minus t infinity into rho infinity, correct. But however, what we are going to do, we are going to do only the dominant term. So, we are going to take this term only associated with this, as we told earlier, okay. So, we are going to take it as rho infinity u dv dx plus v dv dy is equal to mu d square v dx square plus g beta t minus t infinity into rho infinity, okay. Now, if you divide out with the density term now, so what you will get is dv by dx into v dv by dy, this becomes your kinematic viscosity. Kinematic viscosity is still given by the rho infinity, okay. This is given by Gb T minus T infinity, that is what you should get, right. So, that is the expression, that is the expression that you have, right. So, the momentum, entire momentum equation kind of sandwiches and becomes exactly like this, right. So, what are the key things that we have done? We have taken that in the convective term there is no variation in density, density is a constant. In the, on the other hand, in the body force term, what we have done is that we have decomposed the density variation, we have used beta, right, which is the volumetric expansion coefficient. We have done it in such a way that for small changes in density, that means for small changes in temperature, this can be given by a linear interpolation. So, that is exactly what this has been, right. And now we see that the momentum and the energy equations are intricately coupled to each other, because this has got T minus T infinity over here, right. And if you write the energy equation, okay, in this particular case, which is du dt by dx plus v dt by dy is equal to alpha t square by d x square, that will be what it will be, right. Okay. So, that expression you see that there is velocity, of course, that is already given, that they would have the velocity terms. Now, you have the temperature term also appearing in the momentum equation, which was not the case in the case of your forced convection, right. So, this complicates things a little bit. That means the velocity now is also dependent on the temperature to a certain extent, right, and the temperature is also dependent on the velocity. That is obvious, because the heat transfer has got both velocity as well as temperature, right. Okay. So, this complicates the issue a little bit, but we are trying to attempt something like a scaling argument as we have been following. We follow the trend like scaling, similarity, integral, in whatever ways we can provide more insights into the problem, right. So, that brings up to the next part of the argument. Now that we know what the governing equations actually look like with Boussinesq's approximation, if the temperature variation is very large, say 100, 200 degrees Celsius for example, this will not be this simple. You have to solve the full equation, right. You have to solve the full equation, you have to take into account second order effects that comes into the picture, okay, and you have to do a full fledged coupled solution of the whole thing, okay. So, that is also possible in plasmas and other things, okay, you can actually need that kind of an equation. So, let us look at the scaling arguments. Okay. So, let us target the energy equation first, okay, because this is normally what we do. Okay. Now, of course, delta t is given by that delta t, right. Okay. X scales as t as delta t, that we have already shown earlier, v scales as delta t by h, and this will be like delta t by delta t, right. These are the three expressions that you get. Okay. Got it? Okay. So, that is the first thing, the continuity equation therefore equal to 0, right. So, this is given by delta t, u delta t scales as v by h, right. So, this leads to v scaling as u h by delta t, correct. Okay. Now, if you back substitute this particular expression over here now, right, okay. If you back substitute that expression over here, you will find both of them will scale as u over delta t, right. That is usually the case, okay. So, this will scale as alpha delta t by delta t square, okay, or in other words you will get u scaling as alpha by delta t as the first one, and v scales as alpha h by delta t square, right. Remember, your u is the velocity in the x direction, that is the nominal velocity, v is the velocity in the y direction, which is the principal component of the velocity, right. Okay. So, you can see that this is the logic, and you can also see that y u and v, okay, y v will be higher than u, because h by delta t is basically a much larger number, much larger than 1, right. Okay. So, these are the two expressions that you are getting as of now, got it. From the scaling argument, v is proportional to alpha h by delta t square. Now, from the y momentum equation, let us attack the y momentum equation now. Okay. So, y momentum equation, let us write it once again to be on the safe side. Okay. Now, these two will be the same, you know that from your old logic, right, as we did earlier. Okay. So, this will be like v square by h, right, that would be the logic. This will be g beta into delta t, right, that would be the scaling, natural scaling, right. I need not say much about it. This is v divided by delta t square. These are the three expressions, right. This leads to this, this leads to that. Okay. Now, if you substitute for v, which we have already done in the previous page, this one, right. that is alpha h by delta t square, right. So, let us put alpha square h square by delta t square divided by h. This is still g beta into delta t. This is gamma alpha h by delta t square, okay, into delta t square, right. So, that will be the expression, right. Okay. So, or we get alpha square h by delta t square, okay, delta t square. So, sorry, this will be delta t to the power of 4, because, okay, this is g beta into delta t, okay. This is gamma alpha h by delta t to the power of 4. So, what we do, divide everything out by this particular guy, okay. So, if we divide everything out by this particular guy, we will get alpha square h by delta t to the power of 4 g beta into delta t. This will be 1 now, order 1, then gamma alpha h by delta t to the power of 4 into 1 over g beta delta t. Got it? Set of equations that you get, right. Up to this, it should be very clear that why we have got it the way it is, right. So, you just substituted, and but you should know the nature of this term. This term is basically convective, this is basically the buoyancy term, right. This term is basically the viscous term, right. So, you should know that what are the origins of each of the term, that will come in handy a little later, okay. So, now that we can do some manipulations, and we can take this like this, okay. This is alpha square h cube g beta delta t, scales as 1, for gamma alpha h cube, okay. So, that is already something that we have. Now, these terms are looking very awkward, okay. So, let us define something which can make it a little bit more palatable. So, define something called a Rayleigh number, okay. What is the significance of Rayleigh number? Okay, we will see in a little bit. It is g beta delta t, this is the definition, okay, gamma alpha, right. So, that is the Rayleigh number, and we are defining it in terms of h. H is the length scale, okay, in this particular number, right. So, Rayleigh number h. So, now therefore, it becomes h over delta t for Rayleigh number h minus 1, the other one is a Prandtl number, right. So, that is, and then you have 1, and then you have h over delta t raised to the power of 4 Rayleigh number minus 1. So, these two expressions look almost very similar, except that there is a Prandtl number inverse. So, if Prandtl number is equal to 1, then of course, all the expressions are kind of same order, okay. But if Prandtl number is different, very high, very low in the two extremes that we are concerned with, okay, we would have a very different take on the Rayleigh number, okay. Now, if Prandtl number is much greater than 1, this implies that Prandtl number inverse is much less than 1, right. If Prandtl number is much greater than 1, that means Prandtl number inverse is much less than 1. Then what will happen is that the inertia term is which one? This one, right. The inertia term, okay, is negligible, is not that so? So, that would mean that it will be basically a balance between viscous and buoyancy, that means between this term and this term, right. However, on the other side, if Prandtl number is much less than 1, implies Prandtl number inverse is much greater than 1, right. In that particular case, okay, viscous term becomes very negligible, okay, right. Viscous term is negligible, which would mean that inertia is the same as the buoyancy, right. So, that naturally this proves that we have to solve this equation in two ways, in the two limits, in the two extreme conditions. One is for Prandtl number much greater than 1, one is for Prandtl number much less than 1, right. Because depending on the terms that we see over here, that they are very similar except they are differentiated by the Prandtl number, right. So, in the next class what we are going to do is that we are going to take each of these Prandtl number limits, right, and try to work out the problem and see that what are the key features that come out of each of those Prandtl number situations, right. And once we are done with that, then we can move to more formal analysis using integral and subsequently similarity transformations. Thank you.